Good day, students. Welcome to the third lecture recording on Module 6, Reaction Energetics and Food Enzymes. In this section, we're going to focus on the factors affecting the enzyme activity, which are your substrate concentration, the pressure of the system, the temperature, the concentration of the enzyme, the time for the reaction to take place, the pH of the system, and then lastly, the presence of activators and what we call inhibitors. So the first factor that we're going to talk about would definitely be temperature. So before talking about temperature, let's just recap in terms of what an enzyme is. It will then help us understand the role of temperature when a chemical reaction is taking place. So an enzyme is a protein. Proteins are made up of amino acids that are joined together by a peptide bond, and then what happens is that it forms a long polypeptide chain that winds around on its own, whereby it folds, and the folding would be the secondary to tertiary and sometimes quaternary structure. So the highest levels being the tertiary and the quaternary structure would be what we call the native conformation of that protein. That protein functions the best in that shape that it has folded into. So when we come to talk about temperature, we talk about how temperature affects how the enzyme is going to function or how enzyme is going to catalyze the reaction. So each and every enzyme has the minimum, the maximum, and the optimum temperatures that it can actually function. So different enzymes have different temperatures depending on their environment. So what happens is that in terms of chemical reactions, a lot of chemical reaction takes place in an aqueous environment where there is some form of water. So what happens is that at very low temperatures, starting from zero, at very low temperatures, there is actually a very low enzyme activity. And the reason why is that at low temperatures, there are no motions or vibration or movement of molecules. Therefore, for a reaction to take place, the substrate and the enzyme need to collide. But if there's no collision due to no energy at all, then the reaction rates are very low or there's nothing at all. However, by increasing the temperature gradually, what happens is that the temperature increases the kinetic energy that those molecules possess. And what happens is that then that kinetic energy allows those molecules to move and collide. So those will be your enzyme and then the substrate. So then as the temperature increases, then the likelihood of those coming together and forming enzyme substrate complex are quite high. So as the temperature rises, there's an increase in enzyme activity, and that is then shown by the increase in rate of reaction. So what happens there is that at every 10-degree rise in temperature, there's actually twice the reaction of the enzyme taking place. So what happens is that when you increase the temperature, there's an increase in rate of reaction, and then you will be forming more products because now enzyme substrate complex is forming fast because the molecules are colliding. So what happens, this increases up until the temperature gets to what we call the optimum temperature. That's where it's working at its best. However, beyond the optimum temperature, remember we had mentioned that the secondary, tertiary, and quaternary structure are characterized by both your hydrogen bonding, your hydrophobic interactions, your ionic interactions, and so on. So as the temperature now increases beyond the optimal temperature, so what happens is that the enzyme activity is decreasing, because what happens is the hydrogen bonding and other bonding that are formed around the active site are starting to break, because now the temperature has increased up to a point whereby the kinetic energy is too great. There's now molecules are vibrating much faster, up to a point whereby it's no longer just affecting the movement of these molecules to collide, but now it's actually breaking the bonds that are within the enzyme structure itself. So at this point, that is when the enzyme structure changes due to snapping of the hydrogen bonds and other bonds because of the high temperatures. And at that point now, the rate of reaction decreases because now the enzyme becomes denatured up until a point whereby there's no more enzyme activity. So temperature is okay to promote kinetic energy for molecules to collide. But when that kinetic energy increases beyond the movement and collision, what happens is that the enzyme itself now starts changing shape. And then if shape changes, especially on the active side, it means that the substrate can no longer bind in there because now the protein has unfolded. And that's then the effect of your temperature. Okay, so as we already mentioned that the temperature obviously affects the sensitive 3D or three-dimensional structure of the active site. Okay, so high temperatures above 55 degrees Celsius increase the molecular vibration and they start breaking off the weak bonds. By just breaking down the weak bonds, it's affecting the shape of the active site, and then the enzyme become denatured and unable to accommodate the substrate on the active site. So temperature is quite straightforward. And then we come to the effects of pH. Okay, so pH, we spoke about pH the last time when we were talking about proteins. Okay, so let's first see what part of the protein is affected by the pH. So the pH will definitely affect what we called the salt bridges, because remember we mentioned pH is addition of H plus or addition of OH minus. Okay, so by either increasing or decreasing the pH, you add those ions. So it then affects the salt bridge because the salt bridge is between negative and positive. It also affects the hydrogen bonding that's taking place. Remember we also mentioned that hydrogen bonding also takes place between the side chains in the tertiary structure and even in the secondary structure. So what happens? So in terms of enzymes in terms of pH work more or less the same as your temperature. Each and every enzyme has its minimum and maximum and optimum pH ranges. Okay, like your enzymes that are found in the stomach, they are in acidic conditions, so they can work and function there. However, the ones you find in your pancreas, the pH is slightly higher, and even the ones that your amylase that's found in your mouth, it's more basic than it is acidic. So each and every enzyme has got their range of pH they can function in. So what happens when you're adding the pH, or when you're adding H plus, or you increasing the pH by adding acid or adding base? Okay, sorry, by either decreasing the pH by adding acid or increasing the pH by adding a base. So what you need to know is that small changes in pH above or below the optimum does not really cause permanent change to the enzymes, because if there's any bonds, simple bonds breaking, they can be reformed. However, extreme changes in the pH can then cause the enzymes to denature and permanently lose their functions. Okay, so for example, so the addition of acid into, let's assume this is a whole enzyme, and let's say being an enzyme, there is an active site somewhere here, wherever there will be an active site. So what happens is when you add the acid, so the H plus will then go and disrupt the ionic bond there. So you can already see that the H plus will go there to form COOH and not COO minus. So in that way that the net charge there becomes positive, and that bond that was holding those two will then break. So this two chains will snap, and then same applies to if that pH was coming here, whether you are adding hydroxyl group or your proton. This is what's going to happen. The NH3, when you add OH, it becomes NH2, or the COO minus will become COH. So in both cases, this two will then snap. When it snaps, it's actually going to unfold. So the change in pH changes the ionization state, like here and there, and then any other hydrogen bonding that's taking place between these two. So as a result then, when the ionization state changes, there's the shift in the ionic and hydrogen bonding, and therefore any snap or any bond that's being held, if it breaks down, then it changes the whole 3D structure of an active enzyme. And then that obviously will mean that the enzyme has been denatured by adding your acid or your base. Okay, so here's just a graph showing you the different enzymes and their optimal temperatures and optimal pH. So looking at this ones, you have your optimal temperature for most human enzymes, which is close to 37 degrees Celsius. You can see there's an increase up until you get to the optimal temperature, and then a sudden decrease at 50. However, when we're talking about the optimal temperatures of thermophilic bacterial enzymes, look at the lowest temperature. It's 40 degrees Celsius, and the optimum temperature is somewhere at 75 degrees Celsius. And then it denatures completely at 90, which are two different types of enzymes. And then talking about the pH, look at pepsin, that is a stomach enzyme, versus trypsin, which is an intestinal enzyme. So you can already see that the minimum, optimum, and maximum ranges are different for both, because they are found in different areas. So they have different pH requirements. Okay, so that's just a graph showing that. So just a table showing you the different enzymes and their optimal pH. So there's your lipase, it has 8, optimal pH is 8, and your urease is 7, amylase that's found in the pancreas is between 6.7 and 7. So it already shows that if you want to work with a certain enzyme, you need to know its optimal temperature and then optimum pH, which is something we're going to do when we do the effect of temperature and pH on the functioning of polyphenol oxidase in the subject food analysis too. Okay, and then now we come to the part whereby we're talking about the effect of increasing enzyme concentration on the chemical reaction. So when we talk about increasing enzyme concentration, in this instance we need to also note that the increase in enzyme concentration over time increases the reaction rate exponentially. And the reason for that would be, remember we mentioned that enzymes never get used up. The only thing that gets used up are the substrates. So in this instance, we actually have enough substrate all the time. So we keep on adding the substrate. So provided there's enough substrate all the time, there's sufficient substrate being added, the rate of reaction will increase as the reaction time increases. And that will be due to the fact that the substrate concentration is also very high and it's kept going that way. Otherwise, if there's less substrate, then the enzyme activity will go down. So I'll repeat this one. The rate of reaction, or when there's an increase in enzyme concentration, increases exponentially, and this will be only done if, or this will only happen if there's a maximum flush of substrate. So there's consistently addition of substrate all the time, and in that way the graph will look like that. And then what happens when we are increasing the substrate concentration but keeping the enzyme constant? So you need to take in consideration then, now instead of having maximum or infinity enzyme concentration, we actually have a constant enzyme concentration, but the substrate concentration is increasing all the time. So what happens then? Okay, so still remember, reaction rate increases over time. So when you increase the substrate concentration, remember the enzyme never gets used up. The only thing that gets used up is the substrate. But in this case, the substrate is not going to be used up because there's so much of the substrate. There's too much of the substrate. So what's going to happen is that the enzyme might even get exhausted, but let's find out. Okay, so as the substrate concentration increases, there is an exponential increase in the reaction rate up until a point whereby it then reaches the maximum velocity and then it plateaus. Okay, so I'll talk about that again. The effect of substrate concentration. So when the substrate concentration is increased over time, the reaction rate increases exponentially up until a point whereby it reaches the maximum velocity, and then when it gets to the maximum velocity, there's no more increase, it just plateaus. And why does that happen? The reason that happens is that because we have constant concentration of the enzyme, but there's more substrate that needs to be catalyzed. So the enzyme and the substrate complex substrate form the substrate enzyme complex, and then eventually the product. But because there's too much concentration of the substrate, what happens is that at some point in time, all those enzyme sites become saturated. They become saturated with your substrate, and then they are blocked at the enzyme substrate complex because now the enzyme gets overwhelmed. That is when you get to the plateau, whereby above, whether you increase the concentration of the substrate, no reaction rate increases. It just becomes constant. It plateaus, and that's due to the fact that all the enzyme active sites are occupied and saturated. So therefore, the fact that you are increasing the substrate concentration, the reaction rate cannot continue anymore. Okay, so in that instance, that's when we actually have a problem, because now the maximum velocity has actually plateaued. The only way that you can actually allow this reaction to increase exponentially is to add more of the enzyme. But obviously in this instance, we mentioned that the substrate concentration is increasing, meanwhile the enzyme is constant. Okay, so when we have this, we usually then talk about what we call the Michaelis constant. Okay, so what happened in this graph is hyperbolic. Like I already mentioned, at low substrate concentration, there's a straight line, it's rising steeply, and the reaction is in its first order kinetics, because in the first order kinetics, both the enzyme and the substrate are reacting, and everything is exponential. And then when it reaches the maximum velocity, that's where I mentioned that the enzyme becomes saturated. But there, what we do is we can come up with what we call the Michaelis constant, or the Km. Km is what we explain as the substrate concentration at half the maximum velocity. So let's say the maximum velocity was 50. So then it means that the reaction rate where it's half maximum velocity will be 25. So then we actually look at the concentration where of the substrate where the velocity was half of the maximum, where the concentration is half of the maximum velocity. Okay, so when the substrate concentration is at half maximum velocity, we call that the Km, and that's what we call the mixed order kinetics. So why is this Km very important? This Km usually tells us about how fast the substrate actually react with the enzyme. So if you have a very low Km, it means that your enzyme moves very fast and then collide with the enzyme. So it tells you about the affinity of the enzyme. Affinity is love. The affinity of the enzyme to the substrate, how likely they are to meet together and then form a reaction. So it tells you, usually they also use that to check the specificity of an enzyme. If there's two enzymes, which one will first collide with the substrate? So that's what they usually use in chemistry or in food biochemistry. So the Km tells you about the affinity of the enzyme. So a small km means that this enzyme collides much faster and it reacts much faster. It has a higher affinity with the enzyme. That's why it reaches km at low substrate concentration. And when the km is quite large, it means that the enzyme took some time to collide with the substrate, and there might be some reasons for that. We will actually talk about that a bit later on. Okay, so we already started talking about the kinetics, whereby we spoke about the different kinetic orders, enzyme kinetics. So the kinetic orders actually indicates how many molecules are reacting in the slowest step of the reaction. So we have first order, second, and zero order. In the first order reaction, it's a reaction where it depends mostly on the concentration of only one component. The second order, it's a reaction in which two components are reacting together at the same time. And the zero order is actually when the concentration of one reactant is so high, like the one with the substrate concentration being very high, that it remains more or less constant during the reaction. So this reactant can thus be eliminated from the equation. So, and then the reaction then becomes what we call pseudo first order. Okay, so the expression of enzyme activity. So the unit for expression of enzyme activity is known as the Catal. The SI unit is not used. So it tells us about the transformation of a mole of substrate per second by the enzyme. So then enzyme activity is the amount of enzyme that converts 1 micromole of substrate per second. Okay, and then the turnover number will definitely be the number of substrate molecules that were converted by one enzyme molecule under specified conditions. I mean, those are the conditions that we spoke about that affect how the enzyme functions. So when we talk about 10 odd number, we then have to talk about something that was converted at, whether it was at its lowest pH or highest pH, but it has to be at the favorable conditions for that for that enzyme to take place. And then from there, we then what we call activators and inhibitors. An activator is any molecule that would attach to the enzyme, and usually at the active site, and then in turn it will boost the reaction rate or the activity of the enzyme. And then on the other hand, an inhibitor, inhibits, will be any molecule that will then attach itself to an enzyme, thus affecting the reaction negatively. Maybe the reaction can be either slow or doesn't happen at all. So what happens is that both these agents, being the activator and the inhibitor, they affect the protein in a way that it folds in its tertiary structure. Thus, in turn, then affects the shape of the active site. So if the shape of the active site then changes, then the substrate might not be able to even attach. Or, like I mentioned, it can even enhance its activity beyond what it's used to. Okay, so the one thing that we're going to focus more on will be the inhibitors instead of the activators. Okay, so of the inhibitors, there's 3 types of inhibitors, or actually 4. We have what we call competitive inhibitors, non-competitive inhibitors. We also have uncompetitive inhibitors and the mixed type inhibitors, but we're not going to talk about the later 2. What we're just going to focus on will be focusing on the competitive and the uncompetitive or non-competitive inhibitor. Okay, so what are those? So a competitive inhibitor. So a competitive inhibitor will be any compound that resembles the structure and even molecular geometry of the substrate. So it looks like and is shaped like the substrate. So what it does then to actually compete with the substrate is that because of its shape and geometry, it then competes with the substrate for the active site. So it goes and lodges into the active site of the enzyme. However, remember we had mentioned that enzymes are specific. So, and they are specific to certain substrates. So what happens is that when that inhibitor gets into the active site, it just stays there and occupies space, but no chemical reaction takes place because it is not the substrate. but then it's actually blocking the actual substrate from getting in there to be catalyzed, and in that way it can either slow down the reaction or stop it permanently. Okay, so like we mentioned, the inhibitor is stuck on the enzyme and it prevents any substrate molecules from reacting with the enzyme. However, when we talk about this competitive inhibitors, they are usually reversible, and the only time when they are reversible is when the substrate concentration is increased. So by actually increasing the substrate concentration, there is a displacement of that inhibitor. So you increase the substrate concentration and then that inhibitor gets removed from the space, and in that way that's when the reaction will take place, because when the inhibitor moves, the rightful substrate gets in there and the reaction is then catalyzed. Okay, so the amount of enzyme inhibition obviously depends upon the inhibitor's concentration, the substrate concentration, and then obviously the relative affinities of the inhibitor and the substrate to the active site. Which one has got more affinity to the enzyme? And inhibition, this competitive inhibition, is usually applied in terms of how the drugs like your ARVs or your aspirin and all these drugs that you use for diseases or for ailments and all that, that's how they work in competitive inhibition of the enzymes of that bacteria or of that virus. Okay, and then the competitive inhibitor, I found this very funny, so I think you guys are also gonna love it. Okay, and then non-competitive inhibitor. A non-competitive inhibitor is any substance that would interact with the enzyme, but definitely not on the active site. So it will just interact with the enzyme remotely in any other part of the enzyme, but not the actual enzyme itself. However, by doing that, what happens is that even if it attaches to the site somewhere, it then changes the what? The whole 3D dimension structure of the enzyme, and it unfolds or folds differently. But then in that way, the substrate can no longer fit in the active site if it changes. So the effect of a non-competitive inhibitor is to change the shape of the enzyme and thus the active site. So the substrate can no longer interact because now the shape has changed, so there won't be any reaction. So in terms of non-competitive inhibitors, they are usually irreversible. Okay, and they are not influenced by the concentration of the substrate like it is with the reversible. So once that happens on the site, they usually call this allosteric enzyme inhibition. So if that happens, now no matter how much substrate you increase in terms of concentration, it does not matter, because now the enzyme has already been distorted, changed in shape. So increasing the substrate concentration won't do anything on the shape of the active site because it's already denatured. Okay, so here are the enzyme inhibition kinetics. So what's more interesting is we already spoke about the effect of substrate concentration increasing and how it affects the initial rate of reaction. So with the uninhibited graph, which is the green one, we have that normal phenomenon whereby an increase in substrate concentration increases the rate of reaction, and as the rate of reaction increases, the substrate concentration is also increasing, and then until it reaches what we call the maximum velocity and plateaus. Okay, and then we also get the half maximum velocity, and then you get the Michaelis constant. Okay, but look at the competitive inhibitor. With the competitive inhibitor, you can see that it follows the same increase, but the increase is much lower. Okay, so you can see that at the initial rate of reaction is way lower for the blue graph compared to the green graph, and that is because the rate of reaction was quite low. Because remember, if there's an inhibitor that's stuck on the active site of the enzyme, what should happen? We should actually increase the substrate concentration. We should try and increase the substrate concentration to get the inhibitor to displace the inhibitor out of the active site. And in that way, that is why the rate of reaction is much lower, but eventually all the enzyme active sites eventually will be saturated with the same substrate. It's just that it takes a bit longer because we also have to overcome the inhibitor, remove it. So as you can see that, do you look at the Km for the green graph? You can see that the Km is quite low compared to this Km. Remember I mentioned that low Km means there was a faster affinity or reaction or colliding. So the enzyme and the substrate collided much faster, and therefore it means high affinity. But then because of the inhibitor, the Km becomes large because then it takes long for the substrate to actually get into the active site, because remember the active site was locked or blocked. Therefore, that's why the substrate concentration had to be increased to displace that. Okay? And then we get the non-competitive inhibitor, where you can already see that the rate of reaction is quite low and it plateaus much faster, because in any case there was no reaction, or there was little reaction due to the inhibitor that was stuck, that actually changed the active site of the enzyme. Okay, so that's that. So you need to be able to explain this graph with all the different inhibitors. Okay, so just to recap effect of reaction on the substrate concentration, the inhibitors, they compete with the substrate for the active site of the enzyme. When a competitive inhibitor binds the enzyme, the substrate cannot bind, but at high substrate concentration, saturation of the enzyme with substrate will still take place. When an inhibitor is present, the Michaelis constant increases, and the reason why it does so is because you need more of the substrate to displace the inhibitor. The more inhibitor present, the more substrate is needed for half the saturation with enzyme to take place. So the presence of this inhibitor actually causes what we call a sigmoidal instead of an hyperbolic curve. So see the graph that I just showed you now. Okay, so thank you for listening.